All right. Good afternoon. Any question before we start? So we are doing velocity analysis. So we have started with an offset slider crank. So we want to do velocity analysis for the offset slider crank. The first thing that we need to do, we should do the displacement or position analysis first to find the value for the unknowns, which are theta 3 and B or S in this mechanism. For velocity analysis, the unknowns would be the derivative of the variables that we had on displacement analysis. So we are starting for omega 3 or theta 3 and beta. What we did, we just wrote the vector loop equation. First, from the vector loop equation, we derive the x component and y component. This is the x component, y component. Then we differentiate it with respect to time. So the only tricky part was when you want to differentiate the term like this with respect to time. A is constant, it's coming out of the derivative, so we are differentiating theta 2 with respect to time. Since the time is different than this variable, we should use the chain rule. So A, derivative of cosine of theta 2 with respect to the variable that we have here, multiplied by derivative of this variable with respect to time. So this is going to be negative sine of theta 2 times theta dot 2 or omega 2. So when you want to differentiate, you should use the chain rule to get this derivative, negative A omega 2 or theta dot 2 times sine of theta 2. So we did that to derive two equations for velocity analysis. We end up to these two equations. The variables were v dot and theta dot 3. I showed you how can we write the equation in matrix form. We move every term with the unknowns in one side, which are d dot and theta dot 3, and moving the other term to the right side. Then we form three matrices: matrix A, matrix X, and on the right side matrix B. And matrix for vector X, we are going to have our unknowns, which are d dot and theta dot 3. So on matrix X, we are going to have the variables, which are unknowns, which are d dot and theta dot 3. First row representing the first equation. Second row representing the second equation. On this term, we are looking at the coefficient of d dot on the first equation. The coefficient of d dot is 1, we plug in 1. The coefficient of theta dot 3, it's coming here, negative b times sine of theta 3. And right hand side is going for constant part, which is this term. Second row, second equation. This guy is corresponding to the coefficient of d dot. We don't have any d dot, so I'm plugging 0. And b cosine of theta 3 is the coefficient of theta dot 3. It's coming here, and the right hand side is going to have the constant part. In MATLAB, you enter matrix A as 1 negative b sine of theta 3 semicolon, so 0 b cosine of theta 3. B term theta 3 are now is coming from displacement analysis. Theta 3 is the length of link 3. You enter matrix B, which is negative A theta dot 2 sine of theta 2 semicolon A theta dot 2 cosine of theta 2. And here we can find x equals to A backslash B. If you use A backslash B, it's gonna give you the results or the answer of d dot and theta dot 3. If d dot is the first variable that you have here, the first value that you will get here is gonna be for d dot. If theta dot 3 was up, then the first value is gonna be for theta dot 3. Any question before we go through the class activity? Good? All right. So this is doing the velocity analysis for this offset slider crank with A, B, this is D, this is C, and this is theta 2 and theta 3. So suppose this crank is moving at the constant speed. So theta dot 2 is constant. We have powered this link, this mechanism, and it's running at the constant speed. So it's running at the constant speed. So theta 2 is varying over the time. Can I say that d dot and theta dot 3 would be constant as well? At different value of theta 2. So when the mechanism is running at the constant velocity, at any theta 2, at any value of theta 2, theta dot 2 is constant because the input velocity is constant. Can I say that d dot is going to be constant while the mechanism is running at the constant speed?
No.
Why is that? Because theta 2 and theta 3 value are changing in this system of equation. So although theta dot 2 is constant for different value of theta 2, but the value on the right side and the left side are changing. So we will get a different result for d dot and theta dot 3 and different value of theta 2. Good. So it's running at the constant speed, but at different theta 2 we will get different d dot and different theta dot 3. All right, let me work on one simple example. So we are given with this mechanism A is given, B is given, and the offset is given. For A equals to 3, and B equals to 8, C equals to 2. Theta dot 2, the input link is running at 15 radian per second clockwise. And theta 2 is negative 30 degree. So we would like to know when this mechanism is at the angle of negative 30 degree, And theta dot 2 is 15 radian per second clockwise, meaning it's running clockwise direction. Clockwise is negative. So in our equation, we should use theta dot 2 with a negative sign because it's clockwise. What would be theta dot 3 and d dot? What would be the velocity of the slider and what would be the angular velocity of the tree? So in velocity analysis, we should perform displacement analysis first. At theta 2 equals to negative 30 degree, we will get two modes. Theta 3 is going to be first node 205.94 degree, and D3 and not D1, which is the first node, is gonna be 9.8 inch. Suppose the units are in inch, and second node for theta 3 is negative 25.95 degree, and second node for D is negative 4.59. So this is a displacement analysis. We should do it first. So I should perform velocity analysis for both nodes, but in the class I'm gonna do for the first node. We can do the same process for the second node. Just refresh. How did we get the value for D and theta 3? We solve this quadratic equation to find D, and then we plug in those equations and find theta 3. We will get 9.8 and 205.9 for the first one. So I'm working on this. What I need to do, I need to use this system of equation, the matrix form that I got on the previous slide. 1, negative B is 8, sine of theta 3, which is 205.9. I missed the index of 3. 0, 8 cosine of 205.9. The variable is going to be d dot and theta dot 3. On the right side, negative A, negative 3, A is 3. Theta, it should be theta dot 2, not theta 2. Theta dot 2 is negative 15. 15 radian per second clockwise, meaning I should plug in negative 15. Sine of theta 2, sine of negative 30. Second row, A is 3, theta dot 2 again is negative 15, cosine of negative 30. If I do math for these two, I will get negative 22.5, negative 38.97. 1, negative 8 sine of 205, matrix A equals to 1, negative 8 times sine degree, 205.9. Semicolon going to the second row. Say it again.
You put 9205.
Thank you. Parentheses should be. Second row is 0 and 8 cosine. 0 space 8 times cosine degree of 205.9 bracket. So it's going to be the first matrix. Matrix B, which is the right hand side, is going to be negative 22.5 and negative 38.97. Or you can do the same thing that I did to get that matrix by using the method. I'm just plugging negative 22.5, semicolon, and negative 38.97. And this is matrix A, matrix B, A backslash B. I will get negative 41.42 and 5.41. The first value corresponding to D dot, so it's going to be D dot. Second one corresponding to theta dot 3. The unit of this is radian per second. I always use unit for the angular speed by using the radian per second to be consistent. And this one, if the unit is inch, it's going to be inch per second. If it's in centimeter, it's going to be centimeter per second, meter. Whatever is that unit, the speed is going to be that unit over the second. So this is positive. It's telling me that the angular velocity of link 3 is counterclockwise. Good? So do the same thing for the second mode, you will get the response. Any question on this?
Can you go back to the quadratic equation for D?
This one?
Yeah.
So we got it from displacement analysis that we did for offset slider crank. I wrote these values, but the question is how did we get them back to the displacement analysis? We had this quadratic equation we solved for D, and then back to those equations that we derived to find theta 3.
So the M and the N are just the same ones from like the last time we did the...
Yes,
okay.
for the displacement analysis, yeah. I just copied and pasted.
Okay.
This is from just data 3.1?
Theta 3.1, yes. This is for mode 1. You can just repeat with the updated value to get the D dot for the second node and theta dot 3 for the second node. So theta dot 3 is 5.42 radian per second, and D dot is negative 41.42 units per second, whatever is the unit. We used to use the slider program to use the simulating for the velocity displacement. I don't do this anymore. It's a program that's coming with the book. And we used to cover the graphical approach for velocity analysis. I no longer cover that. The analytical is more accurate. So let's go to the next mechanism, which is the 4-bar mechanism. We are going to do the velocity analysis for a 4-bar mechanism. So again, we should perform the displacement analysis first. It's a 4-bar mechanism. This is A, length is B, C, and D. This point is A. This point is B, O2, O4. Yes. The way that I form the vector is in this. So since I labeled the vector in this form, this is going to be theta 2 This is going to be theta 3. This is going to be theta 4. So for displacement analysis, the constants were A to D variables. We have 4 links, 3 of them moving, all 3 are rotational. So the variables are theta 2, theta 3, and theta 4. 3 moving links and all 3 rotating. We don't have any slide. And nouns are constants. Degree of freedom is 1, so one of the variables should be given. Theta 2 is given. So the remaining is going to be unknowns. We solve for theta 3 and theta 4. This is what we did for this place. For velocity analysis, constant would be the same, A to D. I just copy and paste here. Variables, whatever is changing, whatever was variable on displacement analysis, its derivative with respect to time would be variable in velocity. So just put a dot, theta dot 2, theta dot 3, and theta dot 4, or omega 2, omega 3, omega 4. Angular velocity of link 2, angular velocity of link 3, and angular velocity of link 4. So the nouns would be constant plus theta 3, theta 4 would be noun for velocity, and also theta 2. Plus whatever is noun here, put a dot on the top of that, it should be noun. Because the degree of freedom is 1, one of the velocity should be given. So omega 2, whatever is the variable here, its velocity should be noun. We are solving for theta dot 3 and theta dot 4. Any question on this? It's easy because you can compare displacement with velocity just by putting a dot on the variables and the nouns, and you will end up to velocity analysis equation. So if I want to write the vector loop equation, it's going to be O to A, AB, point B has 2 arrows ending to that, equals to O to O4 plus O4B. X component is A cosine of theta 2 plus B cosine of theta 3 equals to D plus C cosine of theta 4. Y component is just change cosine to sine. D, the angle is 0, D sine of 0 is going to be 0. Or you can see we don't have any y component, so it's going to be C sine of theta. This is what we did for displacement analysis to derive the equation for displacement analysis. So now let's do a class activity. I just want to make sure that you know how to differentiate displacement equation and get the velocity equation. So differentiate both sides with respect to time. Velocity is derivative of displacement with respect to time. Differentiate both sides with respect to time. Don't forget about the chain rule. and I will call from the class list. Thursday, that's what the date was wrong, 24. Thursday, 24. Yeah. Number 7. Not. Number 16. What do you think? The first one. Did you think about that?
I thought about it.
And do you have any idea?
No, not really.
We should do the same thing that we did for previous mechanism. The reason that I'm asking you to derive the equation because in homework or in the exam problem you might see something like this to derive the velocity equation. Number 24. That's fine if you make mistake. I just want to see what would be your approach. Yes.
You have to take the derivative?
Yes.
With respect to that, right? So, can I try?
Let me ask someone else then. 21.
Not here. Not here. You're so much.
Okay, what do you think?
So would be negative a times theta 2 times theta dot 2.
Say it again.
Negative a times theta 2 times theta dot 2. Then minus b times theta 3 times theta dot 3 equals negative c times theta 4 times theta 4 dot. And then for the y,
For the second one, I'll finish the second one. Everybody, we are differentiate both sides. So A is constant, it's coming out of the derivative. Theta 2 is different than time. We should apply the chain rule. Derivative of cosine of theta 2 with respect to same variable, which is theta 2, multiplied by d theta 2 over dt, chain rule. So derivative of cosine is negative sine of theta 2. Derivative of theta 2 with respect to time is theta dot 2 or omega 2. They are the same. The first term. Same thing for the second term. B is constant coming out of the derivative. Cosine of theta 3 with respect to time. We don't have same variable, we use the chain rule. B sine of negative B sine of theta 3, theta dot 3. D is constant, is not varying with time. It's gonna be 0. Same thing for cosine of C cosine of theta 4. C is constant coming out of the derivative. Theta 4, just change 2 to 4. You will get sine of theta 4, theta dot 4. And we will get this equation. Second equation, I'm gonna get the velocity equation. A derivative of sine with respect to time is gonna be derivative of sine with respect to theta 2, which is cosine of theta 2, times theta dot 2, plus B derivative of sine with respect to time. We should use the chain rule. Derivative of sine with respect to theta 3, which is gonna be cosine of theta 3, theta dot 3 equals to C cosine of theta 4, theta dot 4. From velocity equation, we could end up to, from displacement equation, we could end up to velocity equation. Question on this. Everybody can see how we differentiate both sides, because I'm going to do this for the next mechanism. For future, for any given mechanism, you are supposed to differentiate from displacement analysis to get the velocity equation. All right, two equations can solve for two unknowns, which are theta dot 3 and theta dot 4. The other terms, which are theta 4, theta 3, are known, coming from displacement analysis. I'm gonna move all terms which are unknown in one side, and the knowns turn to another side. So I'm going to move this to the right side. I will get positive B theta dot 3 sine of theta 3 minus C theta dot 4 sine of theta 4 equals to negative A theta dot 2 sine of theta 2. Same thing for the second equation. C theta dot 4 cosine of theta 4 minus B theta dot 3 cosine of theta 3. Yeah, it doesn't matter which one. Yeah. Thanks. Negative B, I'm going to move to the right side, plus C theta dot 4 cosine of theta 4. Right hand side, the constant part could be this. I did this because I would like to change this to the matrix form. Same as displacement and velocity analysis for offset slider crank, I form three matrix. One matrix A, matrix X, matrix B. Matrix A multiplied by my matrix X equals to matrix B. And this vector or matrix, I'm gonna have two unknowns terms, which are theta dot 3 and theta dot 4. You can write theta dot 4 first and then theta dot 3. It just changes the term that we have here, but it's not going to change the answer. So first row corresponding to the first equation. Second row corresponding to the second equation. First row, this term is representing the coefficient of theta dot 3. Theta dot 3 has b sine of theta 3. B sine of theta 3. Second term is representing the coefficient of theta dot 4. Negative c sine of theta 4. Right hand side is the constant part, negative a theta dot 2 sine of theta 2. Second row, first term representing the coefficient of theta dot 3. Negative b times cosine of theta 2. And c cosine of theta 4. Right hand side is it negative? It should be positive. Thank you. So we are ready to look at matrix A, which has different sign than mine. So as I said, it doesn't matter. Here I kept negative b sine of theta dot 3 in one side and move negative c to the other side. I'm going to get negative b c. Here I multiply this by negative. I got b and negative c here. So as you see, the sign of these three terms are different. It doesn't matter if you put negative on the multiple negative on both sides, you will get the same things. So same thing for the second row. You can either have negative b, positive c, positive a, like here, negative b, positive c, positive a, or negative b, positive c, and positive a. Good? Everybody can see why the coefficients are different in this slide and on the board. So, one quick example. We are given with the velocity analysis of a 4-bar mechanism. The 4-bar mechanism has the length of A, B, C, and D. All are given. The input link, when the input link is at the angle of 57, this angle is 57, angular velocity of link 2 is 10 radian per second. If it doesn't say it's clockwise or counterclockwise, since it's positive, meaning that it's counterclockwise. So we use positive 10. I could say 10 radian per second clockwise, which is going to be negative 10, or I can say just 10, which meaning it's moving counterclockwise.
Would you prefer it as like radians per second or degrees?
Say it again.
Degrees per second or
And radian per second. Always use the radian per second to be consistent. So as I said, we should perform first the displacement analysis. With this input angle, you can solve for theta 3 and theta 4. We may get two modes. One of the modes are given here. The other mode, we don't see it here, but we should do the velocity analysis for the other mode as well. So what I need to do, I just need to plug in the numbers here. B is 6, sine of theta 3 is 16.85. Negative C, which is negative 5. Sine of theta 4 is 121.66. Here I'm going to get negative 6 sine of cosine of 16.85 and positive 5 cosine of 121.66 times theta dot 3 and theta dot 4, negative A, which is 3. Theta dot 2 is positive 10 because it doesn't talk about the direction. So whatever is the sign, I'm using that positive 10 sine of 57. And here, positive 3 times 10 cosine of 57. In the slide is using the system, the matrix form that we derived on the previous slide. So it's going to have negative sign here, positive sign here, and positive sign there. So it's going to get negative, positive, positive. And here it's going to get positive, negative, and negative, positive. Negative of that is going to be negative, so it's going to be this. So you can use the matrix, you can use the MATLAB by using A and matrix B, and then say A backslash B. The result that you will get is going to be negative 4.67 and positive 4 radian per second. It's negative 4, meaning it's a clockwise. If I ask you what would be the direction of rotation, you can say it's a clockwise because it's negative. And it's positive, meaning that the direction of rotation is counterclockwise.
Can I ask why is B sine theta 2 negative there? Opposite here.
This one and this one. So this is representing equation 1. I can multiply negative on both sides of the equation. So I can put negative, positive, and positive. So I can, if you doubt it, I can show on the MATLAB how we get positive of that, negative of this, and negative of this, the same thing here, but the result would be the same. Any question on this? Can we move on the next mechanism? Everybody knows how to use the MATLAB to solve the system equation. I did it for the first problem, for first example. No need to repeat for the second one. Okay. So the next mechanism that we are gonna work on that is offset inverted slider crack. When we have a 4-bar mechanism here, we replace this joint with a slider. With the prismatic or translational joint. Still, we get the 1-degree of freedom. We just replace this rotational joint with the translational. We are going to do the velocity analysis for this one. A, B, C, and D. For displacement analysis, the constants are A, B is not constant because B is changing. So A, C, and D. This length is constant, this length is constant. The variable are theta 2, theta 3. We measure theta 3 at this end. Theta 2, theta 3, theta 4, and beta. The nouns are constant plus theta 2. We are solving for theta 3, theta 4, and b. And we know that theta 3 is theta 4 plus gamma. Gamma is this angle. Whatever is variable here, just put a dot, theta dot 2, theta dot 3, theta dot 4, and b dot. The nouns are constant plus theta 2, theta 3, theta 4, b, and theta dot 2, and we are solving for this tree. The velocity of the slider, or this guy, the angular velocity of link 3, and angular velocity of link 4. So we are gonna do this tomorrow. All right.